All that's between us and drinks is Mark Seager. No pressure.
No pressure.
Formerly.
I know I'm supposed to speak for an hour and a half, right?
You already talked me out of that. That's a good thing. I've known Mark for a number of years as a senior person from Lawrence Livermore. Now I'm proud to say a colleague of mine at Lawrence Livermore and Intel. He'll be talking about the criteria for scalable architecture. Mark is the CTO for Intel's Exascale program and very well positioned to talk about Exascale, and I presume the demands on that from an I/O standpoint. So Mark, welcome.
Thank you. Pleasure to be here. So, when my wife found out that I was asked to give a keynote at the conference tonight, she made sure that we arranged to wear me out prior to this, so I'd be in my best shape addressing you. So she arranged for a 50-mile horseback endurance ride yesterday, and then this morning we had to do the annual humiliation ritual. Anybody out here knows what the Seager annual humiliation ritual? No, it's not giving the keynote at OFA. It's shearing goats at home. So that's what we did first thing this morning. Hopefully the talk tonight will go just a little better than that did this morning. Talk a little bit about the criteria for scalable architectures and beautiful downtown Monterey, California. It's gorgeous out there. I hope you all had a good day and are settling in for the conference. This is our canonical diagram for an Exascale system, and for Open Fabrics Alliance, I'd like to point out the fact that there's multiple networks involved here. I highlight two of them there. The Interconnect for the high-performance Exascale system on the left there, and also a storage area network that ties together not only the Exascale system, but other systems. This is how real supercomputers are used at data centers, high-performance computing centers all across the world. It's not just one machine and one file system. It's typically multiple machines hooked together with multiple or a single parallel file system. One of the most important one is the Lustre parallel file system here. That is a parallel resource. And one of the most interesting aspects is that most of the time when we talk about Exascale systems, we completely ignore the I/O over there on the right. But what we're finding out is that the I/O patterns of high-performance computing systems today are pathologically bad for interconnects in terms of a storage area network. It's typically the case that there's never enough bandwidth here relative to the gateway bandwidth that you have over here, and certainly not enough bandwidth relative to the compute resources and the bisection bandwidth of the interconnect there. There are now new attempts at trying to deal with that situation with new memory technologies, starting off with flash and burst buffers that can be thought of as directly connecting as gateways between the compute and the I/O subsystem. But also it could be part of the I/O subsystem, or it could be part of the compute nodes going forward. So the bottlenecks here are tremendous, and the interconnect patterns that we're seeing on the left here, both in terms of scalability, which I'll talk more about later in the talk, but also for building the systems today are becoming more of a challenge. They're actually dictating the architecture of the systems more and more. The power packaging and cooling solutions and highly integrated interconnects are a central theme in that area. But we can't forget the storage area networks as well. And the pathological behavior of storage area networks are typically many into few in terms of bandwidth and number of connections down there, but also very strange patterns. And these storage area networks typically are not built to purpose. They're typically grown organically at a computer center over time. Typically multiple generations of technology like 10 gigabit Ethernet and InfiniBand are common today. And it's a real mishmash compared to the highly architected, highly known and advanced architectures that interconnect architectures that we see for supercomputers on the left-hand side. So I think that is a challenge for us in the Interconnect community to reach out to our storage colleagues and to make sure that we understand their challenges and the environments that they work in. So at Exascale, we're firmly convinced at Intel that that's it requires a design with a systems focus. And by a system here, I mean a system of systems, not only for the Exascale system, but connecting into high-performance computing data center. And the hardware has to be extremely scalable. And for that, we need as simple of a node as possible and a hierarchical infrastructure. Now, and I've already mentioned in passing some of that hierarchy. The SAN doesn't connect to every compute node. It actually connects through these gateways called operating system nodes with burst buffer capability, as opposed to connecting to all the compute nodes. And we're beginning to see that, as I mentioned, a new storage hierarchy is emerging where we have innovative new memory technologies, most of them non-volatile, that can be placed in the system. And if you think about that, that is going to change the I/O patterns and the communication patterns within the systems, we think, very dramatically. In addition to that, we need scalable system software. And I like to use the term factor and solve whenever you have a forbidding problem, like a 100,000 socket system at Exascale over here on the left with 100,000 copies of the Linux operating system, probably not a good idea for scalability or reliability. We can factor that into two problems. One is we scale down to these operating system nodes here with an order of magnitude or 2 orders of magnitude less copies of the operating system. And then we solve that problem by creating a virtual operating system on the compute nodes and function shipping to the operating system nodes to create the binary compatibility of Linux on the compute nodes. But the actual implementation of that is dramatically different than what we see today. And this can't be done without scalable applications. And what we're seeing over and over again is the demise of the bulk synchronous computation and communication model, as well as the bulk synchronous I/O model. And this is coming about from the needs to control power, from the need to have very aggressive capabilities for not moving the data. And so if power is one of the main factors there, then we're probably going to want to operate on the data as close as possible to where the data is created, so we don't have to spend the power to move it around. That means we're going to be doing visualization and post-analysis of the data in situ, meaning on the compute nodes themselves, or in transit as the data flows out of the machine. And the likely candidate there is the operating system node with burst buffer, which also gives us the capability of doing post-processing of that data either on the compute nodes or on the I/O nodes. And that will dramatically reduce the power requirements. So a lot of people think that Moore's law is running out of gas. That's actually not the reality. We have a research and development program at Intel that sees Moore's law advancing through the end of the decade and beyond. We're, don't do research more than 10 years out, so we can't see beyond that. But through 2020, it looks very good. We're introducing new technology generations over the years. Strain silicon was one of the first ones. High-K metal gate was the next one, and in 2011 we came out with the Tri-Gate or FinFET transistor, which is now the foundation for all of our high-end processors. And this 22 nanometer leap in technology gave us a 37% performance gain at lower voltage and a 50% active power reduction at constant performance. However, Moore's law is not enough. If you look at the impact performance over the years from 1993 through 2013, what we see is in aggregate, which is the top line, the sum of all the systems on the top 500 list, and the top system on the list, there in the green in the middle, and then the bottom system on the top 500 list, all of those curves are going up at twice the compound annual growth rate, CAGR, of the base silicon technology. That means that what we see in LINPACK performance growth is 2x every year, and the performance gains that we're seeing out of Moore's Law, not the Moore's Law transistor law, which is doubling transistors every 18 months at constant cost on a single die. What we're seeing in terms of performance is a little less than that. It's about 2x every 2 years. So where does that other 2x every 2 years come from so that we can keep Moore's Law going at 2x every year? Well, it comes from larger systems. And those larger systems mean more sockets, more processors. That's why Intel is very interested in high-performance computing. But it also means very much larger systems than you see, as you see the Jaguar system there at Oak Ridge. It also means lots more power and new facilities and those kinds of things. And it's also very, and I'll come back to that theme in a couple of minutes, but it's also very interesting to note that whatever is the number one system on the top 500 list, in 6 to 8 years, that performance is basically what is required to be on the bottom of the top 500 list. And even more interesting is, you know, if you reach back far enough, this slide is from Jack Donguera, which he compared to his laptop at 12 gigaflops. That was back in '98, and you know, the iPad 2 and phone book. iPhones are a little less than that, and that dates back to 1995. And back in those days, we were just at the beginning of the killer micro revolution. So in my tenure at Livermore, we fielded a number of systems in the ASCII, the Accelerated Strategic Computing Initiative, and then later ASC program. And these are the systems that we started in 1996 to get to 100 teraflops in 10 years. Spent several $1 billion doing that. We had a progression of systems that kicked it off with the Blue Pacific joint procurement with Los Alamos, and then later ASCII White, and then the Purple and Blue Jeans started, and then the next generation Blue Jeans and Dawn and Sequoia came out. So these systems more than quadrupled the initial one, more than quadrupled the capability computing at Livermore when the Blue Pacific initial delivery system was delivered in 1996. It was a whopping 140 gigaflops, amazing at that point. 512 nodes, single core per processor. Power was 130 kilowatts, which was about 4 times what the Cray YMP required, and that was on the floor where we had a bunch of YMPs and 7600s and other stuff. In order to upgrade that facility, we had to double the power and airflow into that at a cost of about $500,000. So the next system came in, was a little bit more than that. Started with 4-way processors, 4-core processors, a much larger system, and then that became the nucleus of the 3rd generation system. And notice now the power starts to climb, and we ended up, as I mentioned, doubling the power in that building. And then we figured out that the next system wouldn't fit into that building, ASCII White. We were going to jump from almost 4 teraflops to a little more than 12 teraflops, a factor of 3. And notice we did that factor of 3 in less than 2 years. Right, so that's way above Moore's Law. So the number of nodes was reasonable, but look at the number of cores jumped up, and the power to do that system. We had to refurbish the old Nurse facility at Livermore after Nurse moved to Berkeley, and in doing that, we doubled the power in that building to almost 3.9 megawatts. At a cost of about $17.5 million, and also added 50% more floor space. And then we figured out about the time that we were doing that upgrade that, oh, by the way, it wouldn't handle the next machine, and that building couldn't be upgraded anymore either. So the first 2 buildings were out of gas. We needed a new building, and I got to tell you, when my boss, Mike McCoy, found out about that, it took him literally 2 weeks before he stopped calling me crazy. So we spent several years trying to get a building. Los Alamos got a building at about the same time. And that building we specified as 15 megawatts, and everybody thought we were completely crazy. So they cut us back to 12 megawatts, and it turns out that at $96 million, that wasn't enough. So at the end of leading up to delivering Sequoia in the building 453, it required another upgrade, and we upgraded that from 12 in a couple of stages up to 30 megawatts. And I don't know, but if you look at that power number from 130 kilowatts to 8 megawatts, and you draw a line through that, getting to Exascale is going to be pretty tough. So where will technology get us? Well, as I mentioned, Moore's Law is alive and well, so we'll keep advances in silicon technology. And as I mentioned, we'll get 2x density every generation. But, as I mentioned, that's only half the story. The other factor of 2 comes through increasing levels of integration and through architectural discontinuities. And by that I mean new generations of systems. So Blue Gene was an example of that, going to a low power core, and going from tens of thousands to hundreds of thousands. But what we see is that that will continue, and there's another discontinuity coming as well in memory technologies, which will change the I/O story through integrated non-volatile memory. So one of the things, and this is why one of the reasons why I think it's very problematic that the bulk synchronous computation and communication model is in trouble, is that in this curve over here on the right basically says that if you go to very low voltage, which they call near threshold voltage, you can get an efficiency of almost 10x in terms of flops per watt, or data movement per picojoule, all that kind of good stuff. But it comes at the side effect of needing to have much more resilient hardware. You'll have much more frequent errors, and the hardware will need to detect that and correct it if possible, and if not, then hand it up to the runtime system and applications area. And all of that, dealing with those errors, will create a non-deterministic compute environment that is fundamental to the process. So 2 key areas of integration are next. Memory, new bandwidth and density ratios are required. This is needed to compensate for the ever-increasing density of DRAM that is not keeping up in speed. Bandwidth is more fundamental than density. We can trade density for bandwidth, but actually the curve is going the other way. So new technologies are nearing prime time, and on the interconnect, it's time to integrate. Performance, cost, and power all contribute to that, and if we take these two together, that means more stuff closer to the processor. So these curves here are a little bit hard to read, but the one on the left basically shows the exponential increase in computational capability per processor, and the required bandwidth to support that computation. And then what you see underneath it is the actual delivered memory bandwidth that are being fielded in systems. And just to put a really fine point on it, 1 byte per flop is with a good cache system is agreed upon as the ideal, but systems are being fielded today with a very wide divergence of actual delivered memory bandwidth, and that is impacting performance significantly. So we're actually beginning to think that the B to F ratio, as we've looked at it traditionally, is not what we want to be looking at going forward, because now with a proliferation of vector units and especially on GPUs, the B to F ratio for scalar is actually really good compared to the B to F ratio for vector. And if you look at most scientific simulation codes, they don't do a lot of vector. They do a fair amount of vector, and that's all very good. So we're saying fundamentally this ratio is very expensive, and it's getting confused. It's confusing architects in terms of what they should really be focusing on. There are the caching and all that kind of good stuff gets a very high fraction of peak, but yeah, more memory bandwidth is a lot better, but we're beginning to think that if we focused the machine parameters around scalars as opposed to vectors, that you'll be very happy with the overall performance of your machine. It won't typically get as much of the peak delivered performance, so the ratio of peak to vector peak to delivered performance will go down, but the amount of performance that you can get out of your scalar code will go way up. And since that's the slower part of your code, that means your time to solution will actually go down. So we've talked about the B to F ratio for memory, but the same argument can be applied to networks. And here there's a very precious resource in the network, and there is also this proliferation of cores and memory and the performance per socket. Can we trade that off? Can we trade off the amount of performance we put in a socket, meaning go down, and make the interconnect look better, make the memory subsystem that we put on that look better relative to the peak of the socket, and then do scale out, which means you need much larger interconnects, much, as I mentioned, with the new memory technologies, probably better bisection bandwidth in that interconnect. And so that's going to put a different metric on the machine. And this, again, is the philosophy that was inside of Blue Gene, was trade off individual node performance for way more nodes and do that in a highly scalable fashion. So the other thing that we're looking at as part of the Fast Forward project funded by the DOE is looking at DRAM architecture and changing DRAM radically from a single page across a wide section of the DRAM to multiple pages that allow us to do lots of refresh, do fewer refreshes, and actually take most of the data that is read today on the left-hand side, doesn't actually go across the pins, and that's a huge waste of energy in that accessing that array. So we can cut back the power required in DRAM by a factor of 2, we think, or more with this revised technique. And then there are very innovative in packaging and I/O solutions. On the left-hand side, what we've got is processors stacked on top of memory die through silicon vias, connecting the memory elements to the processor, and those together in a multi-chip module. And each one of those now can be thought of as a separate node within a supercomputer, and an interconnect connection going out of that. And what you used to think of as a socket now is actually 4 sockets, and the only real connection out of that socket is via the interconnect. And that's what I meant earlier when I was saying for exascale systems we need the system node concept to be as simple as possible and as scalable as possible. And if we're putting multiples of those inside of a multi-chip package, we're eliminating a lot of PCB connections, a lot of error transmissions between the memory and the processor that go from DRAM through a PCB and ball grid arrays and so forth by doing that. There's another concept where we are interleaving the DRAM die with a higher performance processor on top of it through silicon vias. And again, that gives us, both of these options give us much tighter integration between memory and CPU. And each one of those CPU dies now has an interconnect connection. So as I mentioned earlier, it's time to integrate the fabric connection to the processor. And if we do that, We can decrease the I/O interface tens of watts, which is a major cost advantage when you multiply that by 100,000 sockets. That's tens of megawatts now. It also significantly reduces the cost and improves the density by doing that. And the other thing that you get is much tighter integration with the processor, which means that the latency, the kinds of accesses between the interface, the fabric controller, and the processor can change, which will lead to much greater scalability capabilities. So the other thing that we're seeing in this approach is that it significantly improves reliability of the overall system. Beyond a very short distance between integrated fabric interfaces in the processor, we think there's a need to go to silicon photonics. It's a single chip integrated transmission receiving device that allows us to, with a laser and a waveguide and silicon-based modulator with multiplexer, we can very efficiently and very low cost drive very high-speed interconnects. In the lab, we see this device being able to transmit above 10 gigabits a second. Now, that goes over a fiber optic cable to give us a wide distance, and then the receiving end is the other piece, but it's on the same chip, right? And that can be integrated, that chip can be tightly integrated with the processor in a multi-chip module for a very dense solution. So the next couple of slides are from Livermore. Thanks, Matt, for sending me an update on this recently. This shows all the way up to 10,000 cores, and I really like this slide because it shows that commodity interconnects down here with on Zen are way faster than almost every other machine available, based on either Opterons or Blue Gene up here, with a much slower processor, as I mentioned before. And the scalability of this thing is excellent. But notice that purple curve there. That purple curve is a power system at retirement a couple of years ago. That was a Power 5 system. But this is the thing that I keep talking to my colleagues at Intel about. If you only look up to 1,000 or 10,000 cores or MPI tests, boy, do you really miss the picture. Notice that purple scaling curve over there? It goes boink. And on this curve, you basically miss it, right? It's not great, but it's not the boink you see over here. And again, Zen scales really well. This is the C*2 interconnect on the Cielo system at Los Alamos. And again, what we see is InfiniBand systems doing remarkably well, both in terms of processor performance. The curve over here, the starting point of the curve, is basically single processor performance. And the scalability of commodity interconnects are rivaling that of custom-built interconnects in Blue Gene and also custom-built interconnects from Cray. Now, the other thing that's very interesting to look at is from looking at QDR40 from TrueScale InfiniBand versus the C*2 on Cielo, you see that messaging rate is dramatically better with TrueScale. Again, a commodity interconnect, and it's somewhere between it's 4.5 times better to 2.5 times or 2 times better, depending upon the number of MPI tasks per node, which means the number of cores you're absorbing in the MPI task as you go up goes down, and it's just dramatic in terms of the delivered latency and messaging rate performance out of TrueScale. And that comes about because it's a software implementation. It doesn't use up the hardware resources as much, and we can fan out more of the processing to more of the cores through software. So in summary, now that I'm keeping you from your drinks, I'd like to sit down and listen to your goat roping stories as well. The integration of memory and network into a processor will dramatically help keep us on the path of Exascale. It's not the only thing that we need, but it is a driver for us. Energy is the overwhelming challenge. As I pointed out, you can't, every couple of machine generations, you can't build another building that costs 10 times more than the building before and call that a scalable methodology. The B to F ratios and memory per core, while they have their place in history, can also result to impediments to progress. And we currently think that commodity interconnects can deliver scalability through improvements in bandwidth, latency, and messaging rate. And by integrating that HFI onto the processor die, we're going to get all three of those. So thank you very much. So as a keynote, I try to be as controversial as possible, so Bill will come up and now take all the questions.